So it turns out that in pure water, the concentration of hydronium ions are equal to the concentration of hydroxide ions at 25 degrees Celsius. And we actually have a value for what those concentrations are. So in pure water, both of these concentrations are equal to 1.0 times 10 to the negative 7th molar. This can kind of actually just be quickly written as 10 to the negative 7th. It pretty much means the exact same thing. So concentration is 10 to the negative 7th molar. So we can develop what's called an equilibrium constant to talk about the equilibrium condition of water. So when we're talking about equilibrium, like I said earlier, it's that process of water breaking down into the ions and then those ions coming back to reform the water. And we are not really going to talk about equilibrium in this class, but it's going to come up a lot in AP. So for right now, just trust me that it's a thing, trust me that it exists, and trust me that this is how we write equilibrium constants. So for this one specifically, it's called the ionization constant of water because that is exactly what it's describing. So we're going to call this ionization constant Kw, capital K, subscript W. So Kw is equal to the concentration of hydronium ions times the concentration of hydroxide ions. And this is just a thing. This is describing the equilibrium condition of water. Just take my word for it for right now because we didn't learn about how to write equilibrium constant expressions. So from this, we can find out where our pH scale comes from. We just have to do a little math to figure it out. So we know that Kw is equal to the concentration of hydronium times the concentration of hydroxide, and we have values for those again. So we know that this is equal to 10 to the negative 7th for concentration of hydronium times 10 to the negative 7th for concentration of hydroxide. And this comes out to be Kw is equal to 10 to the negative 14th. So let's think about how we defined pH and pOH up here. We said if we wanted to find these things, we would take the negative logarithm of the concentration of whatever we're trying to find. For pH, we took the negative logarithm of concentration of hydrogen ions. What if I wanted to find pKw? That's totally fine. All I have to do is say pKw must be equal to the negative logarithm of 10 to the negative 14th. So let's use some properties of logarithms to figure out how we can get rid of this logarithm from the equation. So properties of logarithms say that if I want to get rid of a log, I can raise each side of the equation as an exponent using the base of my log. So this log has no base written, which means we must assume that it's base 10. So what I can do is say the left-hand side of the equation, 10 to the negative pKw. Oh, I forgot to mention one thing. You need the logarithm to be on its own in order for this property to work. So your first step would actually be dividing both sides of the equation by -1 or multiplying by -1, doesn't matter, same thing. So you get negative pKw on the left-hand side, and then on the right-hand side, you would just have positive log of 10 to the negative 14th. Then you can do this step. So I'm going to raise both sides of the equation to a power of 10. So 10 to the negative pKw is equal to 10 to the log of 10 to the negative 14th. So what this now does is it basically cancels this term in your equation out. If you don't know properties of logs, or if you don't remember your properties of logs, if you learned them a little while ago, don't worry about it. Just take my word for it right now. Come get help at another time if you want to talk through them. So when I do this, what this now is showing is 10 to the negative pKw is equal to 10 to the negative 14th. Properties of exponents say if your base is the same, your exponents must be equal. So this means pKw is equal to a value of 14. Cool. What does this mean? Why do we actually care? Let's think back to what the expression Kw meant. Kw is equal to concentration of hydronium ions times the concentration of hydroxide ions. What happens if I take the negative logarithm of both sides of these? Negative log of Kw is equal to the negative log of H3O plus times OH minus. Properties of logarithms say that if I have a log expression with something multiplied inside of it, I can separate that out into two logs. If they're being multiplied, I separate it out into two logs being added. So negative log of Kw is equal to negative log of H3O plus log of OH minus. Distribute this negative in right here to this term and to this term, and I end up with negative log of Kw is equal to negative log H3O plus minus log of OH minus. These terms should hopefully look familiar to you. We defined negative log of Kw as pKw. Negative log of H3O plus is defined as pH. Negative log of OH minus is defined as pOH. So what this is telling us is that pKw is equal to pH plus pOH. We found that pKw has a value of 14. So therefore, due to the equilibrium relationship of these ions, pH plus pOH equals 14. So this is where our pH scale comes from. It's on a 0 to 14 scale because of the definition of the autoionization of water at 25 degrees Celsius. So pH and pOH are really just shorthand ways to describe the concentration of hydronium or hydroxide solutions on this logarithmic scale. Logarithmic scales are incredibly important, but they don't just mean if I'm going from a 0 to a 14 and everything's like 1 point away from each other. If you have a concentration of hydronium ions in solution that, let's say, is at pH 1 versus concentration of hydronium ions that would be shown as pH equals 2, what does that actually mean about their concentrations? If they're 1 pH point away from each other, they are tenfold apart in their concentration because logarithmic scales are always increasing in factors of 10. So they are a factor of 10 apart in concentration. pH equals 1 is 10 times more acidic than pH 2. The lower you go on the scale, the more acidic. The higher you go on the scale, the more basic. So this is where our pH scale comes from. It comes from everything we need to know about water. So next we're going to talk about how to actually calculate pH and pOH in solutions.